Welcome everybody. This will be our first example of general substitution method. So it's actually very easy. I'll explain as I do this example. So if you look at this example 1, this is not separable. You cannot really separate. You can try, but you will not be able to do that. It's not linear because if you square it, you'll end up with y square. So it's not linear. And you can check that it is not exact. So none of the method we learned previously will work. But using general substitution, you can easily solve this problem. So the step 1, if you look at carefully, you substitute a new function in place of something. So I'm going to substitute a new variable in place of that inside the parenthesis. So let's do that. So we can call it u or v. I'm just going to call it v. So my v is x plus y plus 1. Here you're thinking v as a function of x, because remember at the end of the day your y is a function of x. So the whole thing on the right hand side is actually a function of x. So here v is a function of x. And because y is unknown, v is also unknown. So our goal is to rewrite this differential equation by replacing the unknown function y by unknown function v. So v will take the place of y. So I have to express all this differential equation in terms of v and x. And hopefully that will be simple to solve for v. But once I know v, I know y. So I'll circle this relation here. It will be very important. We'll come back to this later. But right now, so we have to start with the finding the derivative, right? With respect to x. So let's take the derivative of both sides with respect to x. The derivative of x is 1 plus the derivative of y is dy dx, and the derivative of 1 is 0. So I can forget that. So let's solve for dy dx because I want to know what goes in place of dy dx, right? So I do need to solve for dy dx. So let's solve for dy dx. Subtracting 1 from both sides. So I know that in place of dy dx, I have to substitute this. That goes in place of dy dx. And of course, v goes in place of x plus y plus 1. So let's do that substitution. That's the reason it's called substitution method. It's actually general substitution method. Later on, we're going to specifically see some special types of substitution. For example, homogeneous and Bernoulli. So those are basically some special types of substitution. So if I substitute in place of dy dx, I end up with dv dx minus 1 equal to v square. Remember, in place of x plus y plus 1, that is your v. In this differential equation, v takes the role of y. V is our unknown function. Can we solve for v? It looks simpler than the previous one. So perhaps this is separable. Let's try. So if I bring that negative 1 to the other side, and indeed it is separable. So I can divide both sides by 1 plus v square. If I divide both sides by 1 plus v square, and I can, sorry, and I can multiply both sides by dx. I end up with this. Again, I divide both sides by 1 plus v squared, and I multiply both sides by dx. And of course, there's the invisible one here. So you take this. So this is separable. I have some function of v times dv equal to some function of x times dx. So v takes the role of y. Okay, let's go ahead and take the integral. So the integral of 1 over 1 plus v squared, that should be familiar. So that is the tan inverse of v. And remember, we only add c on one of the side. So I'm going to add c to the other side. So the integral of 1 is x plus c. But we're not done. We have to replace v by what is my v. So my v is x plus y plus 1. So this goes in place of v. So let's go ahead and do that. So I get tan inverse of x plus y plus 1 equal to x plus c. Can we make it explicit? Okay, yes, in this case you can take the tangent of both sides. So if I take the tangent of both sides, then tan and tan inverse will cancel each other. Those are inverse function. So when you compose, you get the identity function. So that will cancel each other. And in this side, you get tan of x plus c. Again, you're taking tan of both sides. You're solving for y. So y is going to be, you subtract x from both sides and you subtract 1 from both sides. So you end up with tan of x plus c minus x minus 1. So this will be explicit solution, and this will be implicit solution. And let's actually graph this in GeoGebra and see how the graph looks like. It's always a good idea to play with the graph, because remember, we're not solving algebraically, we are also analyzing the solution. So let's do a practice here quickly. Forget about that, that's from the previous question. So let's do that. So you start with the c, enter, and that will create a slider, and then my function is tan of x plus c, sorry, yeah, tan of x plus c minus x minus 1. I'm not sure how GeoGebra will handle that. Let me actually put the home. Oh, very good. Not bad, not bad. I'm happy. We expect a graph something like that, right? It should be something like tangent graph, but of course you have this minus x, so that will distort a little bit. Very good. And of course you can play around with this c, because in this case c is inside the parenthesis here, right? So it's somehow slightly, it just move right and left, but it's actually not exactly that, right? It's actually going that way. Wow, it's like a wave function. Very good. And each one, so if I look at for c equal to -4, right? For c equal to -4, right? So that's my solution here. If I move it, that's another solution, that's another solution, that's another solution, and so on and so forth, right? And if I choose a particular point, then it's going to be only one branch that will go through this point. So for example, you know, if I choose a point, maybe here, right? if that's my A, if that is my initial condition. So let's look at the initial condition. So this initial condition means when x is negative 2, y is 4. So that's y of negative 2 equal to 4, right? For that initial condition, what will be my solution? I mean, it is not in the question. I'm creating this. Well, let's go back here and you just play around and see when it touch, right? Right there. Uh, there. And in fact, it doesn't have one solution. So that's one possible solution for the that's the one possible solution for this initial condition. There might be one more. Look at here. Ooh, there's another one. Okay, there's another one coming here. Ooh, oh, because I have negative 5 here, right? So in this case, you can actually play around because you expect this to be some type of periodic function because of this tan. Okay, um, excellent, very good, and always make sure you can do it. Do not forget that. Thank you. Bye bye.